So if Earth was just like a blob in space, not spinning or rotating, then and somehow it was still being heated around the equator more than at the poles, you would have the situation where the air was warming up more at the equator. This warm air would rise up, go through the upper atmosphere back to the poles, and as it travels along here, it's cooling off, and then that cool air would sink at the poles, travel along the surface, continually warming until it got back to the equator, where again it would be very warm and rise. So that would be the situation if the Earth was just a blob and somehow it was being heated all around the equator, and lesser at the poles, but it wasn't spinning. But of course, Earth is spinning or rotating, and because of that, the air at the equator is moving faster because it just has a longer distance to travel than the air at the poles or even in the mid-latitudes. And so as a result, you get the different air currents happening just because you have some air that's moving faster than other air as we move up and down in the latitudes. The diagrams on this slide are, the first one at least on the left, is very similar to what we saw on the last slide. So due to differential solar heating, we said much more solar energy hits the Earth at the equator than it does at the poles, and so we have air warming up much more at the equator than it does at the poles, and that creates this current of warm air rising from the equator, traveling up in the upper atmosphere towards the polar region where it sinks and comes back along the surface. And that happens in the northern and southern hemisphere. But of course, it's not that simple because Earth is rotating, and we saw that at the equator, the air masses are moving faster than they are near the poles. And this causes these air currents to be deflected, which is called the Coriolis effect. And so basically what we see is that air from the equator gets pushed east. So air that's on the northern hemisphere, it's going to travel north and east, and in the southern hemisphere, it's going to travel south and east as you move away from the equator. And so we've discussed the fact that Earth is rotating or spinning, but we didn't talk about the fact that Earth is tilted on its axis. So compared to the sun, I mean, it's all relative. So the axis that goes through the Earth from one pole to the other, it's not aligned perfectly with the sun, and it's on a tilt compared to the sun. And as a result, we get seasons, which we'll see on in the future slide. But this causes some interesting things to develop with our air currents. And also on Earth, we have more land mass in the northern hemisphere than we do in the southern hemisphere. And so this also causes some changes to air currents around the globe, and specifically we see different patterns in the north and the south hemispheres on planet Earth. For our first check-in question, which of the following is not a main driver of atmospheric and thus surface ocean currents? A, Earth is tilted. B, freezing water at the poles. C, Earth is rotating. And D, more land mass in northern hemisphere than southern. So pause the video, take a second, pick your answer, and then come back and I will tell you the answer. Okay, so welcome back. And for this one, the answer is B, freezing water at the poles. So all of the other choices were driving factors in the atmospheric and thus ocean currents. And you can go back to the previous slide if you want to check that out. Okay, what about this one? Air at the equator is moving faster than air at the poles. A, true, or B, false? So pause the video, answer the question, come back. Okay, this one is true. So remember the picture of the Earth with the people on Earth, and it was showing at the equator, that person is moving much faster due to the spinning of Earth than someone at the poles. Okay, so we mentioned this on a previous slide. We talked about Earth's tilt. So compared to the sun and how we travel around the sun, Earth's axis is tilted. And that means that during certain times of the year, different parts of the hemispheres will receive the most sunlight. So we can see that, which means that the summer season is different in the northern hemisphere and the southern hemisphere. So in what we call the northern hemisphere summer, you can see that the tilt causes more of the northern hemisphere to be receiving direct sunlight than the southern. And so that means that the northern hemisphere is experiencing summer, they're getting more sunlight, more intense heating. Whereas in the winter months, the northern hemisphere is tilted away from the sun on its axis, and so it gets less direct sunlight and less solar energy, less intense heating. On the equinoxes, so twice a year, we have an equinox where the north and south, the hemispheres, they both receive the same amount of sunlight, and the most intense sunlight is directly at the equator. So during summer, the most intense sunlight is actually not right at the equator. It's slightly north of the equator. So there's more intense heating going on just north of the equator. And then in the winter, there's more intense heating going on just south of the equator. So if you recall back a few slides where we had our 3 different cells that occurred because of the fact that Earth was spinning, Earth is on an axis, and there's more landmass in the northern and southern hemisphere. We said there was all kinds of stuff that occurred, but we mentioned that there's 3 different atmospheric cells that take place or that are found in the northern hemisphere and then conversely in the southern hemisphere. So if we look at the northern hemisphere in this picture on the left, we see these 3 different circulation cells in the atmosphere, and you'll see that the polar air, what happens is that the cold air sinks at the pole, goes back along the surface towards the northern to mid latitudes, and at that point it's warming up, and so it rises up and starts circling back towards the pole when it gets up into the upper atmosphere. And this happens also at the subtropical latitudes. We see that there's this temperate air pattern where you have cold air sinking in the subtropics, kind of at the same latitude as like the southern part of the United States. It sinks, it warms as it travels along the surface there, and then it rises. And so you get what's called a low pressure system forming in that polar jet stream area. So a low pressure system is associated with cool, moist air, and that's typically what we see in those latitudes around the Great Lakes and Washington State. There's typically cool, moist air in that near that polar jet stream. If we look at the subtropical jet stream, that's where we have cool air that's sinking, and as that cool air sinks, it's warming up and it's losing its moisture as it warms. And so, well, it already had lost its moisture. So with this jet stream, you have air that had moisture in it. As it went up, I can't get the mouse to show on this recording. The warm air goes up away from the subtropics, and as it goes up, you have condensation going on. It rains in the equatorial region near the equator, and it rains at the kind of mid-northern latitudes. And then by the time that air cycles back around and down in the subtropics, that air's lost most of its moisture, and it's heating as it sinks because it's in a warm region. And so as a result, that this subtropical jet stream, that's hot and dry air that we see, and so that's a high pressure system that typically forms. So these 2 jet streams, one is associated with cool moist air and one is associated with hot dry air. And then these jet streams, they move up and down on the globe depending on the season. And additionally, it's important to note which way they're moving around the globe. So they're typically moving from west to east, these jet streams, whereas the air that's at the equator is moving the opposite direction, east to west. And so what you have is there's friction between the air and the water surface in the ocean, and that's what's causing surface currents on the ocean. And the currents are moving different directions depending on the latitude and depending on which jet stream is impacting them. All right, let's check your understanding. So high air pressure systems are typically associated with what type of air? Cold moist air, cold dry air, hot moist air, or hot dry air? Okay, so hopefully you paused and pondered, and you should have come up with hot dry air. So here in Arizona we have a lot of high pressure systems which have a lot of hot dry air. Okay, so based on our jet streams, why is Arizona hot and dry? So well, first of all, pause the video and think about that for a minute and possibly look back at some slides. So in Arizona, we just happen to be at that latitude where you have air. The air has traveled out of the equatorial region where it rained a lot, and by the time the air gets to our latitude, it's lost most of its moisture. And so it descends and it warms up as it descends, and then that's causing a lot of dry, warm air to descend on our latitude, and so that gives us warm, dry air coming down. And then if you look at the cell to the north of Arizona, that also, it's raining up in the northern latitudes from us, so at Washington State, Idaho, all of those are going to get the rain. Then that air is coming back and sinking at Arizona, and again it's warming up as it sinks, and it's very warm and dry. Okay, we're finally getting to ocean currents. So if we just envision what's happening on the scale of air currents, that impacts then how the surface of the ocean water is moving because the air is pulling it along with friction. So we said around the equator, the air currents and thus the ocean currents are all moving from east to west. So along the equator, they're moving east to west on our globe. However, at the mid-latitudes, that air is moving the opposite direction from west to east. And so you get these gyres or circular currents that form because of the equatorial currents moving one direction and then the easterly jet streams moving the other direction. And so also so those equatorial currents, they're going to go west, from east to west, and then when they hit a landmass, they're going to go up or down away from the equator. So that landmass is going to deflect that current, and it's going to go away from the equator. So if you're in the north, it's going to move north. If you're in the south, it's going to go south when it hits a landmass, and then it's going to cycle back going from west to east due to the jet stream currents that are pulling it. So that's what we see, these gyres or circular currents that form in all of the oceans on Earth. And also we see differences in temperature based on this, whether or not the current is traveling from a warm equatorial region or from a cold, more polar region in the gyre. So you can see that the water that's moving from Alaska down the coast of California, that's cold water because it traveled up into the cold latitudes, and then it's cycling back, and it'll warm up as it travels. Then it's going to travel along the equator back over to Japan, travel up the coastline of Asia, and bring warm water along that coastline. Okay, another check-in question. When we're sketching the gyres on Earth, should you always start with which part? So where do you start your sketch? With continental boundaries, the equatorial westerly currents, equatorial countercurrents, or the easterly currents that are around the 50-degree latitude? Okay, so hopefully in your mind you answered B, the equatorial westerly currents. These are those currents that are right along the equator, moving from east to west. The countercurrents would be the currents just north or south of those that are moving counter to those. So one question is, why do these currents matter? And they really do matter because we saw that they take, when you have these gyres rotating, warm water from that goes along the equator, it comes up and it goes across the Atlantic over into Europe. And so Europe gets hit with this warm surface current that keeps it fairly warm compared to its counterparts on the other side of the Atlantic in the northern latitudes. So if you compare the climate of New York City with that of southern Italy is warmer. In the winter, it's getting those warm currents coming up. And similarly with Hudson Bay versus Ireland and Norway, but those areas are warmer over in Europe because they're getting that warm current coming around from the gyre. So here's our next check-in question. The Gulf Stream causes Europe's climate to be what? Warmer than other cities at similar latitudes, cooler than other cities at similar latitudes, or similar to other cities at similar latitudes? Okay, so for this one, the answer should be A, warmer than other cities at similar latitudes.